For as long as humans have existed, the sun has been the most watched object in the sky. Every civilization, every culture, every generation of scientists, with every instrument they could build, all of them pointed at the same object, studying it, measuring it, building models of how it works. For centuries, then decades, then years of increasingly sophisticated observation, the picture seemed to be coming together. Then we actually went there. Not close, not closer than before, inside, through the outer atmosphere of a star, into a region of plasma so hot and so violent that for most of history, the idea of placing any instrument there was not even worth discussing. And the spacecraft that made it, moving faster than anything humanity has ever launched, began sending back data that the models built over those centuries of careful observation had simply not predicted, not on the edges, not in the margins, in the fundamental picture of what the sun is and how it works. There is a question about the sun that has troubled physicists for more than 70 years, a contradiction so basic, so visible, that it should have been impossible to miss, and yet nothing built before this mission could fully explain it. Parker went looking for answers. What it found instead was something stranger than the question it was sent to resolve. The sun we thought we knew and the sun Parker is measuring are not quite the same object. Tonight, we go inside it. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Let's talk about what we actually know. For most of the space age, the greatest obstacle was not distance, it was direction. We often imagine the sun sitting at the center of everything, waiting to be approached, but the reality is far stranger. Every spacecraft launched from Earth begins its journey already moving around the sun at tremendous speed. You and I are doing it right now, carried through space at roughly 107,000 kilometers per hour. That motion becomes a problem. When a rocket leaves Earth, it inherits that orbital velocity. Instead of falling inward toward the sun, it continues racing around it. Escaping the solar system can actually require less energy than reaching the sun itself. The challenge is not acceleration, it is braking. An enormous amount of orbital energy must be removed before any spacecraft can descend toward our star. That was the barrier that stood for decades. To solve it, Parker's solar probe did something that feels almost backwards. Rather than flying directly inward, it repeatedly visited Venus. 7 times across 7 years, the spacecraft passed close to the planet. Each encounter acted like a gravitational brake, stealing a small amount of orbital energy and tightening Parker's path around the sun. Orbit by orbit, the spacecraft spiraled deeper into a region no human machine had ever reached. At the heart of that destination lay the corona, the sun's outer atmosphere. During a total solar eclipse, when the bright solar disk disappears behind the moon, the corona emerges as a pale white halo surrounding the darkness. It appears delicate from Earth, almost fragile, yet hidden within that glow is one of the longest standing mysteries in astronomy. Scientists began studying the corona in 1869. By the 1940s, observations confirmed something deeply puzzling. The sun's visible surface reaches roughly 5,778 Kelvin, while the corona above it climbs to temperatures of 1 million to 3 million Kelvin. The atmosphere was vastly hotter than the surface beneath it. For roughly 80 years, nobody could fully explain why. One physicist spent much of his life trying. Eugene Parker, working in 1958, proposed that the sun continuously releases a stream of charged particles into space. This flow became known as solar wind meaning a constant outward rush of solar material filling the solar system. The idea was controversial. Reviewers nearly blocked publication of his paper. Many researchers considered the concept impossible. Time proved otherwise. Decades later, Parker witnessed a remarkable moment. In 2018, at 91 years old, he watched a spacecraft carrying his name leave Earth. Few scientists have ever seen their own theories transformed into a mission while they were still alive. The mission's destination was a boundary called the Alfvén surface. Named after physicist Hans Alfvén, it marks the region where the sun's atmosphere ends and solar wind begins. Below it, solar material remains connected to the sun. Beyond it, the flow escapes into interplanetary space. Crossing that boundary meant something unprecedented. It meant entering the sun itself. Picture a thin line of shadow moving through a furnace. Everything depends on staying inside it. The spacecraft itself was never designed to endure the full force of the corona. What made the mission possible was a barrier placed between Parker and the sun, a structure known as the thermal protection system, meaning the shield responsible for blocking nearly all incoming heat and radiation before they could reach the spacecraft. At first glance, the shield seems surprisingly simple. It consists of carbon composite foam trapped between two carbon fiber face sheets, creating a layered structure approximately 11.4 centimeters thick. Yet every part of that design emerged from a problem that had no precedent in spaceflight. The choice of carbon was especially unusual. Most materials weaken as temperatures rise. Carbon behaves differently. As it becomes hotter, its structural strength increases. That counterintuitive property transformed it from an ordinary engineering material into the foundation of the entire mission. The finished shield weighs only 72 kilograms, remarkably little, yet it is large enough to cast a protective shadow over every scientific instrument Parker carries. The spacecraft survives not because it resists the sun everywhere, but because it hides behind that moving patch of darkness. Its outer face carries another layer of protection. Engineers coated the sun facing surface with white ceramic paint designed to reflect as much incoming energy as possible. Without that coating, the shield would absorb far more radiation. Temperatures would climb rapidly, and critical components could fail within minutes. But the most astonishing contrast exists just behind the shield itself. On the sun facing side, temperatures can approach 1,400 degrees Celsius. Only centimeters away, the instruments operate between roughly 25 and 35 degrees Celsius. Conditions remain comparable to a comfortable room on Earth. Between those environments lies only a carefully engineered wall. Maintaining that separation requires multiple systems working continuously. A pressurized water cooling loop transports excess heat away from sensitive areas. Passive radiators release energy into space without consuming power. The shape of the shield further reduces exposure by directing intense radiation away from protected components. Nothing about this arrangement could depend on immediate human decisions. Near closest approach, a radio signal traveling from Earth requires approximately 8 minutes to reach the spacecraft. By the time instructions arrived, any mistake would already be over. Parker, therefore, had to become its own guardian. Autonomous guidance systems monitor the spacecraft's position relative to the sun 1,000 times every second. Tiny corrections are constantly applied to maintain perfect alignment. The goal never changes. Keep every instrument inside the shield's shadow. The margin for error is almost unimaginably small. A misalignment greater than a fraction of a degree would expose sensitive hardware directly to solar radiation. Temperatures would rise with extraordinary speed. In that environment, survival is measured not in hours or minutes, it is measured in seconds. At 3:31 in the morning on August 12th, 2018, a column of fire rose from Cape Canaveral and began carrying one of humanity's most ambitious scientific experiments away from Earth. The rocket was a Delta IV Heavy, among the most powerful launch vehicles ever assigned to a research mission. Its task was unusual. Most spacecraft are launched to travel outward. This one had begun a journey inward. The opportunity was narrow. Mission planners were working within a launch window lasting only 65 minutes. If weather, hardware, or timing interrupted that opportunity, the entire mission would have slipped by roughly a year. Orbital mechanics are unforgiving. The positions of Earth, Venus, and the spacecraft had to align with extraordinary precision. Everything happened on schedule. Within weeks, Parker was already moving through interplanetary space at remarkable speed. Just 6 weeks after launch, it arrived for its first encounter with Venus. This was not a visit in the ordinary sense. The spacecraft was using the planet's gravity as a tool. Each flyby carefully altered its trajectory, removing orbital energy and tightening its path around the Sun. The process repeated again and again. Across 7 years, 7 Venus gravity assists gradually reshaped the orbit. With every pass, Parker fell closer to the solar environment it had been built to explore. The mission plan called for 24 increasingly deep solar orbits, each one bringing the spacecraft nearer than the last. But proximity came with velocity. As Parker descended deeper into the sun's gravitational influence, its speed climbed dramatically. By its closest approaches, the spacecraft exceeded every previous record achieved by a human made object. It surpassed the mark established by the Helios 2 probe in 1976 and became the fastest machine ever built, moving at hundreds of thousands of kilometers per hour through the inner solar system. Yet the spacecraft carried more than instruments and electronics. Inside was a memory card containing approximately 1,100,000 names submitted by people around the world. Encoded in silicon, those names traveled toward the corona alongside scientific equipment. Parker also carried a photograph of Eugene Parker and a copy of his 1958 paper describing solar wind, the same paper that nearly failed to reach publication. Human history and scientific history were traveling together. As each orbit unfolded, another challenge emerged. During closest approach, communication conditions became difficult. The spacecraft focused entirely on survival and data collection. Hours could pass without confirmation that everything remained operational. Engineers and mission controllers could do nothing except wait. No commands could help. No intervention could arrive in time. The spacecraft either endured the passage or it did not. Those periods became familiar across the mission. After every close encounter, teams on Earth waited for the returning signal. Only then could they learn whether Parker had survived another descent toward the Sun and whether the data gathered during the passage had successfully made the long journey home. Some milestones happen without anyone noticing. On April 28th, 2021, Parker's solar probe passed through a boundary humanity had pursued for decades. No alarms sounded, no message appeared on a screen announcing success. No one in mission control stood up at that moment, knowing history had just been made. The spacecraft simply continued its journey, gathering measurements as it moved through a region no machine had ever entered before. The realization came later. Months after the encounter, scientists began examining the enormous volume of information returned from the spacecraft. Hidden inside those measurements was evidence that Parker had crossed the Alfvén surface, the invisible boundary separating solar wind from the sun's atmosphere itself. Only then did researchers understand what had happened during that passage. The crossing was not as simple as anyone imagined. Earlier models often treated the Alfvén surface as a relatively smooth dividing line. Reality proved more complicated. Parker moved across the boundary multiple times during a single orbit. The surface shifted and rippled, expanding and contracting as conditions changed around it. Rather than a rigid shell surrounding the sun, it behaved more like a constantly moving frontier shaped by magnetic activity and flowing plasma. That discovery carried important consequences. It revealed that the outer edge of the corona is dynamic, meaning continuously changing rather than fixed in place. The sun's atmosphere responds to events occurring across the star in real time. Boundaries move, structures evolve. The region separating atmosphere from solar wind is alive with motion. Inside that fluctuating zone, the environment changes in a subtle but profound way. The plasma, meaning electrically charged gas composed of ions and electrons, remains gravitationally bound to the sun. It has not yet escaped into interplanetary space. It is still part of the star itself. Crossing into this region was not merely approaching the sun more closely, it was entering material that remained physically connected to the sun. For the first time, instruments operated directly within a stellar atmosphere. Parker measured magnetic field strength, which describes the intensity of magnetic influence surrounding charged particles. It measured plasma density, meaning how much material occupied a given volume of space. Temperature readings were collected alongside particle velocity measurements, revealing how fast solar material moved through different regions. These observations occurred simultaneously across multiple locations inside the corona. The significance extended beyond solar science. Every previous study of a star's atmosphere relied on remote observation. Astronomers examined light, spectra, and indirect signals from a distance. Parker changed that relationship completely. The spacecraft performed in situ measurements, meaning observations made directly within the environment being studied. No mission had ever achieved that before. Not around another star, not around the sun. When scientists finally confirmed the crossing, many compared it to humanity's first landing on another world. The comparison was not about distance, it was about entering a category of experience that had never previously existed. For the first time, a human built object was operating inside the atmosphere of a star, collecting knowledge from within rather than observing from afar. Among all the mysteries surrounding the sun, one stood apart because it seemed to challenge common sense itself. The photosphere, meaning the visible surface from which sunlight escapes into space, has a temperature of approximately 5,778 Kelvin. Above it lies the corona, the vast outer atmosphere extending millions of kilometers outward. There, temperatures rise to between 1 million and 3 million Kelvin. The numbers appear backwards. Imagine stepping away from a campfire and discovering the air becomes hotter with every step. The farther you move from the flames, the more intense the heat becomes. That is effectively what astronomers were seeing when they measured the corona. For decades, the observations seemed to violate intuition and challenge conventional expectations about how heat should behave. The puzzle endured. By the middle of the 20th century, researchers had developed two major explanations. Both involved magnetism, but each proposed a different path for energy to reach the corona. The first became known as wave heating. According to this idea, Alfvén waves travel upward through the sun's atmosphere. An Alfvén wave is a ripple moving along magnetic field lines, similar to a vibration traveling along a stretched string. The sun's surface constantly churns and shifts beneath these magnetic structures. As the waves move outward, they carry energy away from the lower atmosphere. Eventually, that energy is deposited into the corona as heat. The second explanation focused on countless miniature explosions. This became known as nanoflare heating. A nanoflare is a tiny burst of magnetic energy released when magnetic field lines become tangled and suddenly reconnect. The concept was first explored by Eugene Parker and later developed extensively by Eugene Parker himself. Individually, each event is relatively small, but across the sun's immense surface, thousands occur continuously. Together, they could supply enormous amounts of energy. For many years, scientists debated which mechanism was responsible, but the answer turned out to be more complicated than choosing one side. As Parker's solar probe traveled through the corona, its instruments collected measurements that had never before been possible. For the first time, Alfvén waves were observed directly within the environment they were proposed to heat. Researchers measured their amplitude, meaning the size of each wave, their frequency, meaning how often the oscillations occurred, and their energy transfer rates. The data confirmed that these waves were carrying substantial energy upward. At the same time, another pattern emerged. The spacecraft detected brief, localized spikes in temperature and magnetic energy. These signatures matched predictions for nanoflares with remarkable accuracy. Small magnetic reconnection events appeared throughout the corona, releasing bursts of energy exactly where theory suggested they should occur. But neither process worked alone. The evidence pointed toward a combined system in which waves and magnetic explosions cooperate. Energy generated below the corona travels upward through magnetic structures, while reconnection events release additional energy throughout the atmosphere itself. After roughly 70 years of uncertainty, the mystery finally began to resolve. The corona is heated because the sun converts magnetic energy into thermal energy, transforming invisible magnetic motion into extraordinary heat high above its visible surface. Not every discovery arrives as the answer to a question. Sometimes it appears as something that should not be there at all. As Parker's solar probe began transmitting data from its early solar encounters, researchers noticed a strange pattern hidden within the measurements of the sun's magnetic field. The direction of the field would suddenly reverse. Then, moments later, it would return to normal. These reversals could last from a few seconds to several minutes. They appeared abruptly and in surprising numbers. The phenomenon became known as a switchback. A switchback occurs when magnetic field lines bend sharply backward before turning forward again. Instead of extending smoothly away from the sun, the magnetic structure folds back on itself, creating a temporary kink in the surrounding field. The shape resembles a sudden zigzag carved into an otherwise flowing pattern. Hints of similar events had appeared in data collected by earlier spacecraft. Those observations were limited and distant. Scientists assumed the structures were rare, curiosities created somewhere far from the Sunday. Parker's measurements overturned that assumption almost immediately. They were everywhere. The frequency alone was startling. Orbit after orbit, Parker encountered switchbacks throughout the corona. Their abundance suggested they were not minor irregularities, but a fundamental feature of the solar environment. Another pattern soon emerged. Whenever a switchback appeared, solar wind speed increased dramatically. Solar wind, meaning the continuous outward flow of charged particles escaping the sun, suddenly accelerated during these events. Plasma surged forward as the magnetic field changed direction. The connection was too consistent to ignore. Researchers began tracing the structures back toward their source. Earlier theories suggested switchbacks formed far from the sun and simply traveled outward through space. Parker's observations revealed something different. The events originated very close to the solar surface itself. Their roots were embedded deep within regions where magnetic activity was strongest. The leading explanation involves magnetic reconnection. Magnetic reconnection occurs when magnetic field lines from different regions are forced together and abruptly rearrange themselves. In a fraction of a second, stored magnetic energy is released into the surrounding plasma. The process can generate bursts of motion, heat, and acceleration throughout the corona. Switchbacks appear to be one consequence of that release. Rather than acting as passive distortions, they may function as channels carrying energy away from the solar surface. Energy moves upward into the corona and outward into the solar wind through these rapidly evolving magnetic structures. The discovery transformed how scientists think about the sun's atmosphere, but perhaps the broader implication reaches even farther. For decades, solar wind was often described as a relatively steady flow. Parker revealed a far more complex reality. The wind is structured, turbulent, and constantly reshaped by magnetic events unfolding in real time across the Sunday. What reaches the planets is not a smooth stream, but the accumulated result of countless dynamic interactions. That insight may explain another long standing mystery. Solar wind arriving at Earth often comes in uneven gusts rather than predictable flows. Space weather forecasters had struggled to understand why. The answer may have been racing outward from the sun all along, hidden inside these brief reversals of a magnetic field that refused to behave as expected. A stream can appear calm from a distance, while hiding turbulence beneath the surface. For much of modern space science, solar wind seemed relatively straightforward. Solar wind, meaning the continuous flow of charged particles escaping from the sun, was first confirmed by the Luna 1 spacecraft in 1959, only a year after Eugene Parker predicted its existence. The discovery transformed our understanding of the solar system, revealing that the space between planets was not empty, but filled with material constantly flowing outward from the Sunday. A broad explanation soon emerged. Researchers envisioned solar wind accelerating gradually as it moved away from the corona. The process appeared smooth and continuous. Energy spread outward, particles gained speed, and the flow expanded into interplanetary space. For roughly 60 years, that framework remained the dominant picture, but direct measurements told a different story. As Parker's solar probe traveled through regions never previously sampled, it found that acceleration was not occurring as a slow, uniform process. Instead, solar wind gained speed in distinct bursts. These bursts repeatedly coincided with magnetic switchbacks and magnetic reconnection events near the solar surface. The connection was difficult to ignore. Rather than behaving like water steadily leaving a reservoir, solar wind appeared tied to countless localized releases of magnetic energy. Each event injected momentum into surrounding plasma, creating a more dynamic and structured process than earlier models suggested. Parker also identified specific source regions responsible for much of the fastest solar wind. These regions are known as coronal holes. A coronal hole is an area where magnetic field lines open directly into space instead of looping back toward the Sunday. The difference may sound subtle, but it changes how energy and particles escape. Open magnetic pathways provide a direct route outward. The effect is measurable. Within coronal holes, solar wind commonly reaches speeds between 500 and 800 kilometers per second. In other regions, velocities often remain between 300 and 400 kilometers per second. The contrast revealed that not all parts of the sun contribute equally to the solar wind surrounding the planets. Yet another discovery followed. Parker detected particles that retained distinct chemical signatures connected to their place of origin. Chemical signatures are subtle variations in elemental composition that act like identifying markers. By examining these markers, researchers could determine where specific particles had originated on the solar surface. For the first time, the sun became traceable. Instead of viewing solar wind as a blended product emerging from the entire star, scientists could begin linking individual streams to specific locations. Distinct regions produced distinct outputs. The solar wind acquired a geographic structure. That breakthrough carries practical consequences far beyond the corona. The speed, density, and composition of solar wind reaching Earth can now be connected to identifiable surface features on the Sunday. Density describes how much material is packed into a given volume, while composition refers to the mixture of particles being transported outward. Understanding these relationships provides a foundation for more accurate space weather forecasting. What once appeared to be a single outward breath is now understood as a collection of many sources, each contributing its own signature to the constantly changing environment that fills the solar system. Long before Parker's solar probe left Earth, astronomers were searching for something defined by its absence. The inner solar system contains vast quantities of interplanetary dust, tiny particles left behind by asteroid collisions, comet activity, and the ancient processes that built the planets. Individually, these grains are insignificant. Collectively, they form a diffuse cloud stretching across much of the solar system. Every planet moves through it. Yet theory suggested that this cloud could not continue all the way to the Sunday. The reasoning was straightforward. As dust particles drift closer to the sun, temperatures rise dramatically. Eventually, the heat becomes intense enough to vaporize the grains entirely, transforming solid material into gas. If that process occurred as predicted, there should be a region near the sun where dust simply could not survive. Scientists called it the dust-free zone. For decades, it remained a prediction rather than an observation. Telescopes could not examine the region closely enough, and no spacecraft had ever traveled deep enough into the inner solar system to test the idea directly. The concept lingered as one of many theoretical features awaiting confirmation. Parker finally reached the necessary distance. As the spacecraft moved inward, its instruments monitored the density of surrounding dust. Density, meaning the amount of material present within a given volume of space, gradually declined. The change was not abrupt. There was no sharp edge separating dusty space from empty space. Instead, the transition unfolded slowly. Beginning at roughly 19 solar radii from the sun's center, dust concentrations started decreasing noticeably. Orbit after orbit, the environment became progressively cleaner. By the time Parker approached approximately 5 solar radii, the dust had effectively vanished. The spacecraft had entered the long predicted dust-free zone. The result carried significance beyond confirming a decades-old hypothesis. Interplanetary dust interacts constantly with sunlight. As sunlight strikes these tiny particles, some of the light scatters in different directions. This scattering creates the zodiacal light, the faint triangular glow, sometimes visible after sunset or before sunrise along the plane of the solar system. The glow is subtle, but it reveals the presence of material spread throughout interplanetary space. Understanding where that material ends helps astronomers understand how it is distributed in the first place. The dust-free zone provides insight into the architecture of the inner solar system. It helps researchers reconstruct how material moved, accumulated, and disappeared during the formation of the planets approximately 4,600,000,000 years ago. The boundary also offers clues about how other planetary systems may evolve around distant stars. But perhaps the most satisfying aspect of the discovery was its precision. Scientific predictions often require revision when confronted by direct observation. Nature rarely follows expectations perfectly. In this case, however, Parker's measurements aligned remarkably well with theoretical models developed decades earlier. The transition occurred almost exactly where calculations suggested it should. It was a rare, scientific moment. A hidden region, predicted long before the necessary technology existed, had finally been reached, measured, and confirmed, not through inference or approximation, but through direct exploration of the environment itself. Long before we understand something visually, we often recognize patterns through sound. The sun itself is silent. Space contains no atmosphere capable of carrying ordinary sound waves between a source and a listener. If you were somehow floating beside the corona, you would hear nothing at all. Yet, Parker's solar probe revealed something unexpectedly close to a voice, not because sound exists there naturally, but because information can be translated. That translation begins with an instrument package called fields. Fields measures fluctuations in electric and magnetic fields throughout the corona with extraordinary precision. A fluctuation is simply a change over time. As charged particles move, collide, and respond to magnetic forces, they create complex patterns in the surrounding environment. Parker records those patterns continuously as streams of numerical data. Numbers alone can be difficult to interpret. To make the information more accessible, scientists convert selected measurements into audio frequencies. Audio frequencies are vibrations that fall within the range human ears can detect. The resulting recordings are not literal sounds traveling through space. They are electromagnetic oscillations translated into a form we can hear. The transformation produces something remarkable. NASA released several recordings generated from Parker's observations. Plasma waves, meaning ripples moving through electrically charged gas, create one set of signatures. Magnetic switchbacks generate another. Even transitions between different regions of the solar environment produce recognizable changes. One recording became especially important. When Parker crossed the Alfvén surface, the data revealed a dramatic shift in behavior. The chaotic crackling associated with solar wind turbulence suddenly diminished. In its place emerged a smoother and more organized pattern. The recording captured the transition from the outward flowing solar wind into the corona itself. The change was unmistakable. Switchbacks sound different. Their signatures appear as sharp bursts and abrupt spikes within the audio stream. Each spike corresponds to a rapid reversal in magnetic field direction. What appears in scientific graphs as a magnetic event becomes, after conversion, something resembling a sudden percussion strike. But these recordings are more than public outreach. Scientists actively use them as analytical tools. The frequency of a signal, meaning how often a pattern repeats, contains information about surrounding conditions. Amplitude, meaning the strength of a signal, reveals additional details. Together, these measurements help researchers estimate plasma density and temperature within regions the spacecraft is passing through. Patterns become clues. Listening to the data can sometimes reveal transitions that are difficult to notice immediately through visual inspection alone. Boundaries, disturbances, and unusual events often produce distinctive signatures. Researchers compare these signatures across different observations, identifying recurring behaviors and physical processes. In that sense, The recordings serve a purpose similar to a stethoscope. A physician listens for patterns that reveal conditions hidden inside the body. Solar physicists listen for patterns hidden within streams of electromagnetic data. The goal is not music or entertainment, it is diagnosis. Yet, the recordings carry an emotional quality that scientists themselves have acknowledged. Many have described them as haunting, not because they were designed to be dramatic, but because they originated in a place no human being can ever visit, transformed from invisible forces moving through the atmosphere of a star. Distances in space often sound abstract until we place them beside something familiar. We can say that Parker's solar probe approaches the Sun more closely than any previous spacecraft, but the true scale becomes clearer when we examine the numbers themselves. During its closest planned encounters, the spacecraft travels to approximately 6,160,000 kilometers above the Sun's visible surface. In astronomical terms, that distance corresponds to roughly 8.5 solar radii, a solar radius being the distance from the Sun's center to its visible edge. That may still seem far away. But consider Mercury. Mercury is the closest planet to the Sun, following an orbit that brings it to roughly 77 million kilometers from the star at its nearest point. Parker travels more than 12 times closer than any planet ever does. The spacecraft enters a region where no natural world resides and where conditions become increasingly extreme. The view changes dramatically. From Earth, the Sun occupies only a small portion of the sky. At Parker's closest approach, the Sun appears approximately 23 times larger than it does from our planet. The familiar solar disk expands into an immense presence, dominating the spacecraft's surroundings, and the energy becomes overwhelming. Solar energy decreases rapidly with distance, which means moving inward produces enormous increases in radiation intensity. At closest approach, Parker receives approximately 475 times more solar energy than a spacecraft positioned near Earth. Every exposed surface experiences conditions far beyond those encountered by most missions. Yet the instruments continue operating normally. Temperature sensors, particle detectors, and magnetic field instruments remain functional despite the environment around them. Their survival serves as a direct demonstration of the effectiveness of the spacecraft's thermal protection system. The engineering is no longer theoretical. It performs exactly as intended under the harshest conditions humanity has ever deliberately explored. Speed rises as well. Near closest approach, Parker exceeds 690,000 kilometers per hour. That velocity corresponds to approximately 0.064% of the speed of light. Although still far below relativistic speeds, it remains extraordinary by human standards. To place that motion into perspective, the spacecraft could circle Earth's equator in less than 4 minutes. Its trajectory, however, is not a continuous plunge toward the Sunday. Parker follows a highly elliptical orbit, meaning an elongated path that repeatedly carries it inward and outward. After each close solar encounter, the spacecraft swings back toward the orbit of Venus before beginning another descent. Each journey takes approximately 88 days. The rhythm repeats again and again, with every pass refining humanity's understanding of the solar environment. The final planned encounters during 2024 and 2025 brought Parker to distances no human-made object had ever intentionally achieved around a star. The achievement is remarkable, not because Parker touched the Sun once, but because it repeatedly returned to a place that had long seemed permanently beyond reach. Every image of the Sun taken before Parker shared the same limitation. The cameras were always looking inward from a distance. Parker changed that perspective completely. Mounted on the spacecraft is an instrument called WHISPER, short for Wide Field Imager for Solar Probe. Unlike traditional solar observatories that view the sun from far away, WHISPER operates from within the environment it is observing. The camera does not merely photograph the corona, it photographs the corona while moving through it. The difference is profound. From Earth, the corona often appears as a faint halo, visible only during total solar eclipses. From Parker's position, the atmosphere reveals an entirely different character. Vast structures stretch across space in intricate patterns shaped by magnetism. These formations are known as coronal streamers. A coronal streamer is a massive structure of plasma guided by magnetic field lines extending millions of kilometers outward from the Sunday. In WHISPER images, these streamers appear as luminous plumes suspended against the darkness of space. Some resemble sweeping sheets, others narrow into rays and filaments. Their forms are not random. Invisible magnetic fields organize the plasma into recognizable patterns that shift and evolve over time. Nothing remains still. The corona revealed by Parker is dynamic and constantly changing. Bright eruptions emerge unexpectedly. Expanding clouds of plasma move outward through the solar atmosphere. These events include coronal mass ejections, enormous releases of magnetized material capable of traveling across the solar system. WHISPER records them from within the environment itself. The instrument also provided a remarkable view of something much closer to home. Parker photographed the zodiacal light band, the faint glow created when sunlight scatters from interplanetary dust. From Earth, we see this glow from outside the dust cloud. Parker observed it from within, offering an entirely new perspective on the structure of material filling the inner solar system. That perspective became even more valuable during a planetary encounter. In 2021, during a Venus flyby, WHISPER captured images that surprised researchers. The instrument detected thermal emission, meaning heat radiated from the planet's surface. Using near-infrared wavelengths, the camera effectively peered through portions of Venus's dense cloud cover. The result was unexpected. Surface features became visible. Rock formations and elevated highland regions appeared in the images. Many of these structures had previously been mapped primarily through radar observations. What began as a gravity assist maneuver produced an additional scientific discovery. But the most striking aspect of WHISPER's images remains their sense of scale. The usual perspective is reversed. We are accustomed to seeing the sun as a distant object occupying a small part of the sky. From Parker's vantage point, the star dominates the scene. The corona stretches outward in every direction. Magnetic structures span enormous distances. Bright plasma fills much of the spacecraft's visual environment. The sun is no longer a remote destination. It becomes a surrounding landscape, vast, active, and far more intricate than any view from Earth ever suggested. Some of the most powerful explosions in the solar system begin with a rearrangement of invisible magnetic fields. The result is known as a coronal mass ejection. A coronal mass ejection is a vast eruption of magnetized plasma launched outward from the Sunday. Plasma, meaning electrically charged gas composed of ions and electrons, is carried into space along with enormous quantities of magnetic energy. These events are the largest explosive phenomena regularly produced by our star. Their scale is difficult to comprehend. A single large coronal mass ejection can contain roughly 10 billion tons of plasma. Some travel at speeds approaching 3,000 kilometers per second. Within a matter of hours or days, the expanding cloud can cross enormous distances throughout the inner solar system. For decades, scientists watched these eruptions from afar. Telescopes and space observatories tracked their growth against the backdrop of space, revealing their overall shape and motion. Valuable information emerged from those observations, but an important limitation remained. Researchers could only examine the exterior appearance of the event. It was similar to studying a hurricane from satellite imagery alone. You could see the storm, you could measure its size and movement, but you could not directly sample the conditions inside it. Parker changed that. As the spacecraft moved through the corona, it encountered the wake of multiple coronal mass ejections. For the first time, instruments were positioned inside regions affected by these immense eruptions. Instead of observing from a distance, researchers could directly measure the internal environment. The data revealed remarkable complexity. Parker recorded magnetic field orientation, meaning the direction in which magnetic forces were aligned throughout the structure. It measured plasma temperature and density, revealing variations in heat and material concentration. The spacecraft also detected intricate turbulence inside the ejections, showing that their interiors were far less uniform than simplified models had suggested. These measurements matter because coronal mass ejections do not remain near the sundae. Some travel outward on trajectories intersecting Earth's orbit. When that happens, interactions with Earth's magnetic field can produce geomagnetic storms. A geomagnetic storm is a disturbance caused when solar material compresses and energizes our planet's magnetic environment. The consequences can be significant. In 1989, a geomagnetic storm triggered by a coronal mass ejection contributed to the Quebec blackout. Approximately 6 million people lost power for as long as 9 hours. Electrical systems designed for ordinary conditions suddenly faced forces generated by activity occurring millions of kilometers away. History contains an even more dramatic example. In 1859, the Carrington event produced the most powerful geomagnetic storm ever recorded. Telegraph systems failed across multiple regions, and auroras appeared in unexpected locations around the world. Modern analyses suggest that a comparable event today could produce economic damage measured in trillions of dollars. But prediction remains the most effective defense. Parker's measurements from inside these eruptions are improving the models used to forecast their behavior. By understanding their internal structure, scientists can better estimate how they evolve, where they travel, and how strongly they may interact with Earth. For the first time, humanity is not merely watching these solar storms form. We are learning how they work from the inside. Invisible shields rarely attract attention until they begin to bend. At this very moment, Earth exists inside a magnetic enclosure known as the magnetosphere. The magnetosphere is the region of space dominated by Earth's magnetic field, forming a protective barrier that deflects much of the charged material constantly flowing outward from the sundae. Every satellite, power grid, communication network, and navigation system operates within this protective bubble. Without it, our technological world would face a far harsher environment. Solar wind never stops pushing. The continuous stream of charged particles presses against the magnetosphere every second of every day. On the side facing the sun, that pressure compresses the magnetic field to a distance of roughly 65,000 kilometers. On the opposite side, the field stretches outward into a vast magnetic tail extending millions of kilometers into space. Most of the time, the system remains stable. But stability is not permanence. When powerful solar disturbances arrive, conditions can change rapidly. Coronal mass ejections and intensified solar wind compress and distort the magnetosphere, producing geomagnetic storms. A geomagnetic storm occurs when solar energy enters Earth's magnetic environment and triggers large scale magnetic disturbances. The effects reach surprisingly far. Energetic particles can penetrate to lower altitudes than usual, interfering with radio communication systems and creating electrical currents in long conductors. Pipelines, transmission networks, and power infrastructure can all experience unexpected stresses generated by activity originating on the Sunday. Navigation systems are affected as well. Global Positioning System satellites rely on signals passing through Earth's upper atmosphere. During moderate solar storms, changes in atmospheric conditions reduce positional accuracy. For aviation, maritime operations, and military systems, even small errors can create significant operational challenges. The impact extends into orbit. Astronauts aboard the International Space Station monitor solar activity carefully. During intense particle events, crews may move into better shielded sections of the station to reduce radiation exposure. The station itself remains protected, but heightened solar activity can temporarily increase risks for people living beyond Earth's atmosphere. Satellites face another problem. Solar storms heat and expand the upper atmosphere. As atmospheric density increases, satellites in low Earth orbit experience greater drag. Drag is the resistance created when an object moves through a surrounding medium. Increased drag gradually alters orbital paths and can shorten operational lifespans if not properly managed. These vulnerabilities explain why forecasting matters so much. The earlier scientists understand an approaching solar disturbance, the more time operators have to protect sensitive systems. Power companies can prepare, satellite controllers can adjust operations. Astronauts can take precautionary measures. This is where Parker's contribution becomes especially important. By measuring solar wind structures and coronal mass ejections closer to their origin than ever before, the spacecraft provides data that improves forecasting models. Researchers can study how disturbances form rather than waiting until they approach Earth. Current warning times for major impacts often range from roughly 15 minutes to 1 hour, but improved models built from Parker's observations may eventually extend those forecasts to many hours or even days. For a civilization increasingly dependent on technology, that extra time could prove extraordinarily valuable. Borders on Earth are drawn on maps. Borders in space are often invisible, discovered only when something crosses them. The Alfvén surface is one such boundary. Named after physicist Hannes Alfvén, it marks a transition between two fundamentally different regimes surrounding the Sunday. On one side, the star remains connected to its atmosphere through magnetic forces. On the other, that connection breaks down, allowing material to escape into the wider solar system. The distinction is subtle but important. Below the Alfvén surface, plasma and magnetic fields remain tightly linked. Plasma, meaning electrically charged gas, moves in concert with magnetic structures threading through the corona. If a disturbance occurs, information can travel back toward the sun through those magnetic connections. In a physical sense, the atmosphere remains in communication with the star. The sun still holds influence there. Above the boundary, conditions change. Plasma begins moving faster than magnetic disturbances can propagate through the surrounding environment. Communication effectively breaks down. The magnetic field can no longer exert the same level of control over the escaping material. At that point, the outward flow becomes solar wind. The transition is not marked by a visible line. For many years, Scientists imagined the Alfvén surface as something roughly spherical, surrounding the Sunday Parker's measurements revealed a far more complex reality. The boundary is irregular, corrugated, and constantly changing shape. Rather than resembling a smooth shell, it behaves more like a shifting landscape influenced by magnetic activity throughout the corona. Its location varies as well. Depending on solar conditions, the boundary can exist anywhere between roughly 10 and 20 solar radii from the Sun's center. During periods of heightened activity, the surface expands outward. During quieter intervals, it contracts inward. The result is a moving frontier rather than a permanent border. This has an unexpected implication. The answer to a seemingly simple question, where exactly does the sun end, does not remain constant. The location changes over time. The star's effective atmospheric boundary expands and shrinks as solar conditions evolve. Parker encountered this reality directly. During several close approaches, the spacecraft crossed the Alfvén surface multiple times within a single orbit. The crossings occurred not because Parker repeatedly changed course, but because the boundary itself moved around the spacecraft. The shifting surface swept across Parker as magnetic and plasma conditions changed. Each passage generated valuable information. Researchers recorded the precise timing and location of every crossing. Over time, these measurements accumulated into something that had never existed before, an empirical map based on direct observation rather than theoretical prediction. Empirical simply means derived from measurements rather than assumptions. The significance extends far beyond our own star. Magnetic fields and stellar winds exist throughout the galaxy. Other stars likely possess analogous boundaries, separating magnetically controlled atmospheres from freely escaping plasma. Understanding how the Alfvén surface behaves around the Sun provides a framework for studying similar transitions elsewhere. It may even help us understand distant worlds. Many exoplanets orbit within the magnetic environments of their parent stars. By understanding where stellar influence changes and how plasma escapes into surrounding space, physicists gain tools for modeling interactions between stars and planets across the galaxy. What Parker mapped around the Sun may ultimately become a guide for interpreting countless other systems far beyond our own. The most valuable discoveries in science are often the ones nobody was looking for. Parker's solar probe was designed to answer long-standing questions about the corona and solar wind. It succeeded, but as the data accumulated, something else emerged. The spacecraft repeatedly encountered phenomena that existing models either underestimated, misplaced, or failed to predict entirely. The sun turned out to be stranger than expected. One surprise involved energetic particles. These are charged particles accelerated to extremely high speeds by solar activity. Prior models suggested such particles should become abundant only farther from the sun, after specific acceleration processes had enough time and distance to operate. Parker found them much earlier. The spacecraft detected energetic particle events surprisingly close to the solar surface. Regions that theoretical frameworks considered relatively quiet contained particles carrying far more energy than anticipated. The observations suggested that acceleration mechanisms were operating more efficiently and closer to their source than researchers had believed. That was only the beginning. Solar wind itself appeared far less orderly than many models implied. Earlier descriptions often treated the outward flow as relatively smooth on large scales. Parker revealed a far more intricate reality. Distinct streams moved alongside one another. Boundaries separated neighboring flows. Mixing zones formed where different regions interacted. The solar wind resembled a dynamic landscape. Instead of a uniform outflow, the spacecraft encountered structures layered within structures. Conditions could change significantly across surprisingly short distances. Temperature, velocity, and composition varied in ways that challenged simplified descriptions. The corona showed similar complexity. Measurements revealed dramatic fluctuations in plasma density. Density describes how much material occupies a given volume. In some regions, Parker observed abrupt transitions between dense plasma and far thinner plasma, separated by remarkably small distances. Existing models predicted variation, but not at such extreme levels. The magnetic field offered another surprise. Remote observations had always hinted at complexity near the Sun, but Parker measured that complexity directly. Fine-scale magnetic structures appeared throughout the environment. The level of detail exceeded what previous observations could resolve from afar. The closer we looked, the more structure appeared. Then came an observation that seemed particularly puzzling. On multiple occasions, Parker detected plasma moving briefly back toward the Sunday. This was unexpected because solar wind is generally defined by outward motion. The dominant flow should be away from the star. Yet some material appeared to reverse direction. Researchers now believe these events are linked to magnetic reconnection occurring at extremely small scales. Magnetic reconnection is the process through which magnetic field lines break and reconnect, releasing energy in the process. Models had acknowledged tiny reconnection events, often called micro-reconnection, but generally treated them as minor contributors. Parker suggested otherwise. The cumulative influence of countless small events may play a larger role in shaping solar behavior than previously recognized. Processes once considered negligible may contribute significantly to energy transfer and plasma dynamics throughout the corona. But none of these discoveries represent failures of scientific understanding. They represent something far more valuable. Every unexpected observation identifies a place where reality contains additional detail. The models were not wrong so much as incomplete. Parker provided the missing measurements, revealing where the next generation of stellar physics must become more precise. The Sun did not violate the rules. It simply showed us how much more there is to learn about them. Some scientific discoveries begin with new instruments. Others begin with a person willing to trust an idea before anyone else does. Eugene Newman Parker was born in 1927 in Houghton, Michigan. He would spend most of his professional life at the University of Chicago, building a career devoted to understanding the behavior of the Sunday. At the time, much of interplanetary space remained mysterious. The region between the planets was often imagined as largely empty, a quiet vacuum interrupted only by occasional particles and radiation. Parker saw something different. In 1958, he submitted a paper to the Astrophysical Journal proposing that the Sun continuously emits a stream of charged particles flowing outward in every direction. Today, we call this flow solar wind. At the time, the idea challenged conventional assumptions about the structure of the solar system. The reaction was immediate. Reviewers argued that the concept violated accepted understanding. Some regarded the proposal as physically impossible. The prevailing view held that interplanetary space could not support the type of continuous outflow Parker described. The paper nearly disappeared. Its survival depended on an extraordinary decision by the journal's editor, Subramanian Chandrasekhar, who would later receive the Nobel Prize in Physics, examined the work and disagreed with the reviewers. He overruled their objections and approved publication. History moved quickly afterward. Within 2 years, The Luna 1 spacecraft provided evidence that solar wind was real. Parker's prediction was confirmed before many members of the scientific community had fully accepted it. What began as a controversial theory became a fundamental part of modern space physics. Yet Parker's influence did not stop there. In 1972, he proposed another bold idea. The corona remained far hotter than the visible surface beneath it, and no convincing explanation existed. Parker suggested that countless tiny magnetic explosions occurring across the sun could collectively provide the required energy. These events became known as nanoflares. A nanoflare is a small burst of magnetic energy released through magnetic reconnection. Individually, such events are modest. Together, Parker argued, they could heat the corona to extraordinary temperatures. Decades later, spacecraft observations would reveal evidence supporting that vision. He also helped establish the theoretical foundation for Alfvén waves as a mechanism for transporting energy through the solar atmosphere. Long before direct measurements became possible, Parker recognized their potential importance. His predictions often arrived years before the technology needed to test them. Then came a rare honor. In 2017, NASA announced the Parker Solar Probe mission. Eugene Parker attended the press conference in person. It was the first time the agency named a mission after a living scientist, acknowledging not only his discoveries but the enduring influence of his ideas. He witnessed the launch the following year. Eugene Parker died on March 15, 2022, at the age of 94. 14 months earlier, the spacecraft carrying his name had crossed into the corona for the first time. The theories he spent a lifetime developing were no longer abstractions. They had become measurements taken inside the sun itself. After spending so much time examining the sun up close, it becomes natural to ask whether our star is unusual or ordinary. The answer is both. Astronomers classify the sun as a G-type main sequence star. A main sequence star is one that generates energy primarily by fusing hydrogen into helium within its core. The designation G-type refers to its temperature, color, and overall physical characteristics. Within the vast population of stars, this places the sun somewhere near the middle of the distribution, neither exceptionally large nor exceptionally small. Only about 10% of the stars in the Milky Way belong to the G-type category. That makes the sun common enough to have many relatives scattered throughout the galaxy, yet uncommon enough that most stars are actually something else. Most stars are smaller. The dominant stellar population consists of red dwarfs, also known as M-type stars. These dim, compact stars account for roughly 70% of all stars in the galaxy. Although smaller than the Sun, they often possess remarkably active magnetic environments. Their behavior can be surprisingly intense. Red dwarfs frequently produce powerful flares and energetic stellar winds. A stellar wind is the equivalent of solar wind, a continuous outflow of charged particles escaping from a star's atmosphere. While the underlying process appears similar, the intensity can differ dramatically from one star to another. For planets orbiting nearby, the consequences are significant. Many red dwarfs host planets within their habitable zones, the region where temperatures may allow liquid water to exist. But because these stars are cooler, habitable zone planets must orbit much closer than Earth orbits the Sunday. That proximity places them directly within regions of strong magnetic activity. Space weather becomes a constant presence. A world orbiting a red dwarf may experience conditions thousands of times more intense than those encountered on Earth. Repeated bombardment by energetic particles and magnetic storms could influence atmospheric stability, surface radiation levels, and long-term habitability. This is where Parker's discoveries gain broader importance. The spacecraft was built to study our own star, but the physical processes it revealed are not unique to the Sunday. Evidence increasingly suggests that corona heating may arise from a combination of Alfvén waves and nanoflares across many stellar environments. Alfvén waves transport energy through magnetic fields, while nanoflares release energy through countless small magnetic reconnection events. Different stars may vary in scale, but the underlying machinery appears familiar. If the same mechanisms operate across diverse stellar types, then Parker's measurements become a foundation for understanding far more than a single star. The observations provide a framework for interpreting magnetic activity, stellar winds, and atmospheric interactions throughout the galaxy. The implications continue outward. Every star exists within an environment shaped by its magnetic field and flowing plasma. Every planetary system develops beneath those influences. By understanding how the sun generates and manages its magnetic energy, we gain insight into processes unfolding around countless other stars. What began as a mission to explore our nearest star has become something larger. Parker's findings are helping transform the sun from an isolated subject of study into a reference point for understanding how stars everywhere interact with the space surrounding them. For most of human history, the sun appeared eternal. It rises, it sets, seasons pass beneath its light. Across generations, the star seems unchanged. Yet, stars have lifetimes just as planets do, and Parker's measurements become more meaningful when placed against the immense timeline of stellar evolution. The Sun is approximately 4,600,000,000 years old. That age places it near the midpoint of its main sequence lifetime. A main sequence star generates energy by fusing hydrogen into helium within its core. The process is stable, efficient, and remarkably long-lived. For billions of years, it has powered the sun's steady radiance. But no fuel lasts forever. In roughly 5 billion years, the hydrogen supply in the core will become depleted. As the internal balance changes, the sun will begin transforming into a red giant. A red giant is a star that expands dramatically after exhausting the hydrogen that once sustained its core fusion. The expansion will be enormous. Current models suggest the sun may grow to nearly 200 times its present diameter. The familiar star that now occupies a small portion of our sky would swell into a vastly larger object, dominating the inner solar system. What happens to Earth remains uncertain. Some calculations indicate the sun's outer layers could extend to Earth's current orbital distance. Other models suggest a different outcome. As the sun expands, it will also lose mass. Reduced mass weakens gravitational attraction, allowing planetary orbits to drift outward over time. Two competing effects emerge. Expansion pushes danger outward. Orbital migration pulls Earth away. The final outcome depends on the balance between those processes. Current studies suggest that engulfment and survival remain roughly comparable possibilities. But Earth's challenges begin much sooner. Long before the red giant phase arrives, the sun's brightness will gradually increase. In approximately 1 billion years, solar luminosity may become high enough to initiate large-scale evaporation of Earth's oceans. Luminosity refers to the total energy emitted by a star. Even relatively small increases can produce profound long-term effects on planetary climates. The future of Earth is therefore connected to the future of the Sunday. This is where Parker contributes something unexpected. The spacecraft was built to study present conditions, yet its observations help improve models reaching billions of years into the future. By measuring solar wind directly, Parker reveals how the sun currently loses material to space. The numbers are substantial. The sun sheds approximately 1.5 million tons of mass every second through solar wind. Over immense spans of time, that loss accumulates. Compared to the sun's total mass, however, it remains a surprisingly small fraction. Precision matters. Even subtle differences in mass loss influence long-term calculations of stellar evolution. Small uncertainties become significant when projected across billions of years. Parker's measurements help reduce those uncertainties by replacing assumptions with direct observation. The spacecraft cannot witness the sun's distant future. Neither can we. Yet by understanding the star with greater accuracy today, we gain a clearer view of what lies ahead for the sun, for Earth, and for every world orbiting within the inner reaches of our solar system. Some missions leave behind discoveries. Others leave behind tools that continue shaping the future long after the original journey ends. Parker's solar probe belongs to both categories. The spacecraft was built to survive conditions no previous mission had encountered. In solving that challenge, engineers created technologies whose influence now extends far beyond solar science. The mission's scientific findings may transform our understanding of stars, but its engineering achievements are already influencing how future systems are designed. The most obvious example is the heat shield. Protecting a spacecraft while it travels through the sun's outer atmosphere required unprecedented thermal engineering. The solutions developed for Parker demonstrate new approaches to managing extreme temperatures. Similar challenges appear in hypersonic flight, where vehicles move through Earth's atmosphere at extraordinary speeds. They also arise in nuclear fusion research and atmospheric entry systems designed for future exploration missions. Heat is a universal problem. Lessons learned from Parker's thermal protection system are therefore valuable wherever materials must survive environments that push them toward their physical limits. The spacecraft's autonomy represents another breakthrough. At close solar distances, communication delays make immediate human intervention impossible. Parker must continuously monitor its own orientation and respond without waiting for instructions from Earth. The spacecraft evaluates its position relative to the Sun approximately 1,000 times every second, making corrections whenever necessary. It effectively watches itself. That capability represents a significant advance in autonomous spacecraft operations. Future missions, traveling into similarly challenging environments, will increasingly rely on comparable systems capable of independent decision-making. The instruments themselves contributed innovations as well. Every sensor had to fit behind a relatively compact protective shield. This requirement drove advances in miniaturization. Miniaturization simply means reducing size and mass while maintaining or improving performance. The resulting instruments became smaller, lighter, and more sensitive than many earlier designs. The challenge extended to information management. Parker collects far more data than it can immediately transmit to Earth. Bandwidth limitations force the spacecraft to prioritize, compress, and organize information efficiently. Data compression reduces file size while preserving scientific value. Techniques refined during the mission have influenced broader approaches to handling large scientific datasets across space research. Even the trajectory left a lasting impact. The mission's 7 Venus flybys demonstrated how gravity assists can reshape an orbit dramatically without requiring enormous amounts of additional fuel. A gravity assist uses the motion and gravity of a planet to alter a spacecraft's trajectory. Parker's flight path has become a reference model for missions requiring extreme orbital changes using existing propulsion technologies. The project also reflected international cooperation. Contributions came from teams at the University of Michigan, Johns Hopkins Applied Physics Laboratory, the University of California, Berkeley, and numerous partner institutions. The mission demonstrated how large scientific efforts increasingly depend on expertise distributed across multiple organizations and countries. But the legacy reaches beyond engineering and science. More than 1 million names traveled aboard the spacecraft. Mission data became publicly available. Audio recordings derived from solar measurements invited people into the experience of discovery. Together, these choices established a powerful model for connecting robotic exploration with the public imagination. Parker explored the sun, but the technologies, methods, and partnerships it created will continue traveling far beyond the mission itself. One of the quiet truths of science is that every solved mystery tends to reveal several more waiting behind it. Parker's solar probe transformed our understanding of the Sunday. Long-standing questions about coronal heating, magnetic activity, and solar wind now have clearer answers than ever before. Yet the mission also illuminated the edges of our knowledge with unusual precision. The unknowns became easier to see. Take nanoflares, for example. Evidence strongly suggests these tiny magnetic explosions contribute to heating the corona. But a deeper question remains unresolved. What determines exactly when and where a nanoflare occurs? Scientists understand the general process of magnetic reconnection, yet predicting why one region suddenly releases energy while another remains stable continues to be extraordinarily difficult. The trigger remains elusive. The Alfvén surface presents another challenge. Parker crossed this boundary multiple times and constructed the first direct map based on observation, but that map follows only the spacecraft's path. We still lack a complete three-dimensional picture of the structure surrounding the entire Sunday. Large portions remain uncharted. Switchbacks raise similar questions. Researchers now understand that these magnetic reversals originate near the solar surface and play a role in transporting energy outward. Yet, no comprehensive theory fully explains why they exhibit particular sizes, lifetimes, or occurrence rates. Their behavior follows patterns, but the deeper causes behind those patterns remain uncertain. The fastest solar wind presents another puzzle. Some streams exceed 700 kilometers per second. Parker has narrowed the list of possible explanations and identified important contributing processes. Even so, scientists cannot yet account for every aspect of the acceleration mechanism responsible for the highest observed velocities. The sun's magnetic cycle remains equally important. Approximately every 11 years, the global magnetic field reverses polarity. North becomes south, south becomes north. This cycle influences solar activity across the entire star. It affects sunspots, eruptions, solar wind structure, and conditions throughout the corona. Researchers understand many components of the process, yet the complete chain of causes and effects remains incomplete. Time is essential. Solar cycles unfold across decades. Understanding long-term behavior requires observations spanning multiple generations of spacecraft and instruments. No single mission can witness every stage with sufficient detail. Parker itself faces limits. The spacecraft carries a finite supply of fuel. Eventually, it will no longer be able to maintain precise orientation relative to the Sunday. When that happens, its scientific operations will come to an end. The mission's data archive will remain invaluable, but new measurements will cease. Fortunately, exploration continues. The European Space Agency's solar orbiter is already operating in coordination with Parker. Unlike Parker, Solar Orbiter follows a trajectory that will gradually provide direct views of the Sun's polar regions. Those poles are among the least explored areas of the solar environment and may hold answers to several outstanding questions. That partnership reflects something fundamental about discovery. Parker did not complete the story of the Sunday, it refined the questions. It replaced uncertainty with more precise uncertainty. And in doing so, it showed exactly where future explorers should look next, not because science failed to find answers, but because it succeeded in finding better questions. Sometimes, the most powerful discoveries emerge not from a single observer, but from two observers looking at the same event from different places. That idea sits at the heart of one of modern solar science's most ambitious partnerships. While Parker's solar probe descended deep into the Sun's outer atmosphere, another spacecraft was beginning its own journey through the inner solar system. On February 10th, 2020, the European Space Agency launched Solar Orbiter, a mission designed not to replace Parker, but to complement it. The two spacecraft occupy very different roles. Parker ventures inward, directly sampling the corona and solar wind. Solar Orbiter remains farther away, where cameras and remote sensing instruments can operate safely while maintaining detailed views of the Sun itself. One spacecraft feels the environment, the other watches it unfold. Together they create something neither could achieve alone. When Parker detects a burst of energetic particles, a magnetic switchback, or a sudden change in solar wind conditions, Solar Orbiter can often identify the exact region on the Sun responsible for producing it. Scientists can connect a measurement taken inside the solar atmosphere with a visible feature on the solar surface. Cause and effect become linked. This coordinated strategy transformed solar observations into a kind of three-dimensional investigation. Instead of merely observing consequences far from their source, researchers can follow activity from its origin, through its evolution, and into surrounding space. Material measured by Parker can be traced back to structures photographed by Solar Orbiter at nearly the same time. The result is remarkable. For decades, solar physics relied heavily on either direct measurements far from the Sun or remote observations from a distance. The combination of Parker and Solar Orbiter bridges that gap. One mission provides context, the other provides contact. But Solar Orbiter carries a unique advantage of its own. Its orbit is gradually tilted relative to the Sun's equator. Every previous spacecraft viewed the Sun from roughly the same flattened perspective occupied by the planets. Solar Orbiter slowly climbs above that plane, gaining angles that humanity has never possessed before. The destination is the poles. These regions play a central role in shaping the Sun's magnetic field and regulating the approximately 11-year solar cycle. Vast polar coronal holes, regions where magnetic field lines extend outward into space, produce much of the fast solar wind that flows across the solar system. Yet the poles remain among the least understood areas of the Sunday. Future observations are expected to reveal magnetic structures that scientists have theorized for decades but have never directly seen. Those observations may reshape current models, describing how the solar magnetic field reverses and rebuilds itself over time. What emerges from this partnership is a new philosophy of exploration. Rather than isolated missions pursuing separate goals, Parker and Solar Orbiter function as components of a coordinated scientific system. One spacecraft enters the environment, the other maps the source. Together, they reveal a star, not as a distant object, but as a connected and evolving process unfolding across space in real time. There are moments in history when a boundary that seemed permanent quietly disappears. For thousands of years, every culture looked upward and found stars beyond reach. They guided sailors across oceans, anchored calendars, inspired stories, and shaped entire cosmologies. Yet, no matter how carefully we observed them, they remained distant lights. You could measure them, name them, and eventually understand aspects of their physics, but you could never cross the gap separating observer from object. That assumption lasted until Parker. The spacecraft did not land on the Sunday, it did something stranger. It entered the sun's atmosphere and moved through material that still belonged to the star itself. For the first time, a human made object passed through solar plasma while remaining operational, collecting measurements from within an environment that had previously existed only as a target for remote observation. The distinction matters. Looking at a star through a telescope reveals light that has traveled across space. Spectrometers separate that light into colors and wavelengths, allowing scientists to infer temperature, composition, and motion. Those methods transformed astronomy into a rigorous science, but they remain observations from the outside. A different threshold was crossed here. When Parker measured magnetic fields, particle velocities, plasma density, and temperature, it was not studying a star from afar, it was immersed within the system being measured. The data came directly from the surrounding solar atmosphere. In a very literal sense, the spacecraft experienced conditions that had never before been experienced by any instrument built by our species. The difference resembles the transition from viewing a coastline to entering the sea. Both approaches reveal truth, yet they reveal different kinds of truth. One describes appearance, the other describes participation. As Parker traveled through the corona, every sensor operated inside material, originating from the sun itself. The spacecraft survived only because decades of engineering created a protective barrier between delicate instruments and temperatures capable of destroying unshielded matter almost instantly. Humanity remained far away. Its machines did not. That distinction carries an unusual significance. The achievement belongs to a small collection of milestones that fundamentally altered our relationship with the cosmos. Leaving Earth's atmosphere changed our understanding of place. Landing on another world changed our understanding of distance. Sending spacecraft beyond the outer planets changed our understanding of scale. Touching a star changed something else. It changed proximity. For the first time, a star ceased being an object observed exclusively from the outside. It became an environment that could be entered, measured, and explored. But perhaps the most remarkable aspect of the accomplishment is how it occurred. No crew guided Parker through the corona. No pilot corrected its course during critical moments. The spacecraft navigated danger alone, monitoring its position, protecting itself, and making rapid decisions beyond the reach of real-time human control. A machine built on Earth traveled into a star's atmosphere and returned knowledge from within it. In doing so, it transformed one of humanity's oldest symbols of distance into something unexpectedly tangible. Before we can understand whether a world can support life, we must first understand the star that surrounds it. Habitability is often discussed in terms of distance. A planet sits within a favorable zone, receives the right amount of warmth, and maintains conditions where liquid water might exist. Yet distance tells only part of the story. A planet also exists within a stream of particles, magnetic fields, and radiation flowing outward from its parent star every second. That flow matters enormously. The sun continuously releases solar wind, a stream of charged particles moving through the solar system. Around other stars, similar outflows are known as stellar winds. These invisible currents interact with planetary atmospheres for millions and sometimes billions of years, gradually shaping the environments that life would depend upon. We have already seen the consequences nearby. Mars once possessed rivers, lakes, and a substantially thicker atmosphere. Evidence gathered by multiple missions suggests that its global magnetic field disappeared early in its history. Without that magnetic protection, solar wind gained direct access to the upper atmosphere. Over immense spans of time, atmospheric particles escaped into space, leaving behind the colder and thinner world we see today. Venus followed a different path. Although it orbits closer to the Sun, Venus retained a massive atmosphere. Solar wind still interacts with it continuously, but the outcome depends on far more than magnetic shielding alone. Atmospheric composition, density, chemistry, and interactions with incoming particles all influence the result. The relationship between stars and planets is not governed by a single rule. It is a system. That complexity becomes even more important when we look beyond the solar system. Parker's measurements close to the source of solar wind provide the most detailed picture ever obtained of how stellar outflows begin, accelerate, and evolve. Those measurements allow researchers to build more realistic models describing how winds from other stars affect orbiting planets. The implications are significant. Most known potentially habitable planets orbit red dwarf stars, the small and extremely common stars that dominate our galaxy. These stars can remain active for extraordinarily long periods. Their magnetic behavior often produces stronger flares, denser particle streams, and more intense stellar weather than our Sun generates. Some worlds may face relentless exposure. A notable example is the planetary system around the red dwarf star, TRAPPIST 1, located roughly 40 light years from Earth. At least 3 planets orbit within a region where temperatures may permit liquid water. Yet, models suggest the system's stellar wind environment could be dramatically harsher than Earth's. Can such planets retain atmospheres long enough for life to emerge? That question remains open, but Parker provides part of the answer. By revealing how solar wind behaves at its origin, the mission supplies a physical foundation for estimating how atmospheres survive, erode, or adapt around distant stars. The search for life is often imagined as a search for planets. Increasingly, it is also becoming a study of stars. Every potentially living world exists within a stellar environment, and understanding that environment may determine whether a planet remains habitable at all. In that sense, Parker's journey into our own star reaches far beyond the Sunday. Its measurements help us evaluate the prospects of life across the galaxy, one stellar wind at a time. Consider, for a moment, the imbalance around which everything in our planetary neighborhood revolves. We often picture the solar system as a collection of worlds sharing space together. Planets circle the Sunday moons, circle planets. Comets wander through the darkness. The image feels balanced, almost democratic, yet the reality is astonishingly lopsided. The Sun contains approximately 99.86% of all mass in the solar system. Everything else combined accounts for the remaining fraction. Every planet, every moon, every asteroid, every comet, every grain of dust drifting between worlds. Together, they represent only a tiny remainder compared with the star at the center. The scale continues to grow stranger. More than 1 million Earths could fit inside the Sunday. In fact, the volume ratio approaches roughly 1.3 million to 1. If our planet were reduced to a small marble, the Sun would still tower nearby as an immense sphere capable of swallowing countless copies of that marble before nearing capacity. And all of that matter is active. Every second, deep within the solar core, nuclear fusion converts hydrogen into helium and releases an extraordinary flood of energy. The amount generated each second is often compared to roughly 100 billion nuclear bombs detonating simultaneously. Yet only a tiny fraction reaches us. Earth intercepts approximately one part in 2 billion of the sun's total output. That almost unimaginably small share illuminates continents, drives weather systems, powers ocean circulation, and fuels nearly every ecosystem that has ever existed on our world. Life has run on that fraction for roughly 3.8 billion years. Even the sunlight touching your skin follows a journey difficult to imagine. The light arriving at Earth at this moment departed the solar surface about 8 minutes and 20 seconds ago. But the energy carried by those photons began much deeper inside the star, far deeper. Most of that energy originated in fusion reactions approximately 100,000 years ago. After being created, it spent immense spans of time scattering through the radiative zone, a region where photons are repeatedly absorbed and re-emitted. Eventually, the energy entered the convective zone, where rising and sinking currents transported it toward the surface. Only then did it escape. Every photon that warmed a human face, nourished a forest, powered the water cycle, or illuminated a civilization began its existence in that inaccessible interior. No spacecraft has ever approached it. No instrument ever will. The core remains hidden beneath layers of plasma extending outward across hundreds of thousands of kilometers, but the outermost layers proved far from simple. When Parker entered the corona, it encountered a region that decades of theory had struggled to explain completely. Magnetic fields twisted unexpectedly. Plasma behaved in ways models had not anticipated. Long-standing mysteries yielded answers while new questions emerged in their place. The spacecraft reached only the outer edge of the Sunday. Yet even there, at the threshold of a star that dominates our entire system, reality turned out to be richer, more intricate, and more surprising than generations of scientists had imagined. Step outside on any ordinary day, and it is easy to overlook the connection. The ground beneath your feet feels solid and independent. Trees seem rooted in the soil. Rivers appear to flow because gravity directs them downhill. Animals move according to their own needs and instincts. Human civilization surrounds itself with machines, buildings, roads, and networks that seem entirely separate from the sky above. Yet, beneath this apparent complexity lies a remarkably simple truth. Almost everything happening on Earth's surface is ultimately powered by the same source. The story begins long before our planet existed. The carbon atoms that form human bodies, forests, oceans of microscopic life, and countless living things were forged inside ancient stars that lived and died before the sun was born. Those atoms provide the material of life. But material alone is not enough. What animates that material now is energy arriving continuously from our star. Consider every green leaf on Earth. Through photosynthesis, a process that converts sunlight into stored chemical energy, plants capture incoming solar radiation and transform it into sugars and other molecules. Those molecules become stems, roots, fruit, seeds, and entire ecosystems. The chain extends everywhere. Animals consume plants directly or consume other animals that once consumed plants. Every calorie moving through a food web can ultimately be traced back to sunlight that reached Earth's surface. Every muscle contraction, every heartbeat, every migration across land or sea is connected to energy that began its journey at the Sunday. Even seemingly ancient energy sources tell the same story. Coal, oil, and natural gas are often viewed as separate categories of fuel. In reality, they represent sunlight stored across immense spans of geological time. Long ago, living organisms captured solar energy through photosynthesis. Their remains accumulated, were buried, compressed, and chemically altered. When fossil fuels burn today, that ancient sunlight is released in moments. The atmosphere follows the same pattern. Wind emerges because sunlight heats Earth's surface unevenly. Different regions warm at different rates, creating pressure differences that move air across continents and oceans. The breeze you feel on a coastline, the circulation of global weather systems, and even powerful storms originate from that continual solar input. Water moves for the same reason. Sunlight evaporates ocean water into the atmosphere. Vapor rises, cools, condenses, and falls again as rain or snow. Rivers flow. Groundwater accumulates. Lakes refill. The entire hydrological cycle operates because solar energy continually lifts water against gravity before gravity returns it to the surface. Ocean currents also participate in this exchange. Surface heating influences temperature differences across vast distances, helping shape circulation patterns that redistribute energy around the planet. Seen together, the picture becomes difficult to ignore. Nearly every process involving growth, movement, weather, climate, or biological activity represents solar energy changing form. It arrives from a distance of roughly 8 light minutes, then spreads through ecosystems, landscapes, and civilizations in countless transformations. That is why understanding the sun matters so deeply. When we study its wind, its magnetic activity, and its atmosphere, we are not examining a distant object alone. We are studying the engine that powers the living surface of our world. Long before equations described stellar fusion or spacecraft crossed interplanetary space, people were already paying attention to the same source of light that rises above us each morning. They had practical reasons. Seasons determined harvests, daylight governed travel, warmth shaped survival. Across continents separated by oceans and millennia, human societies arrived at a similar conclusion. The sun was not merely another object in the sky, it was the foundation beneath daily existence. Ancient Egypt provides one of the clearest examples. The solar deity Ra occupied a central place in Egyptian thought, not because its people lacked sophistication, but because they correctly recognized a profound dependence. The annual rhythm of agriculture, the growth of crops along the Nile, and the warmth that sustained life all traced back to the sun's presence overhead. Their theology reflected an observation grounded in experience. The pattern appeared elsewhere. Across the plains of prehistoric Britain, generations invested enormous effort constructing Stonehenge. Long before written records emerged in the region, its stones were aligned with the summer solstice sunrise. Each year, the returning alignment marked a dependable moment within a larger cycle. The monument became a way of tracking celestial regularity through architecture rather than text. Far across the Atlantic, civilizations developed similar relationships with the sky. The Aztecs built a calendar system tied closely to solar motion, allowing agricultural activities to follow predictable seasonal changes. At Chichen Itza, architectural alignments connected the structure of temples with the timing of the equinoxes. These observations transformed sunlight into knowledge and knowledge into survival. The sun served as a clock. It served as a calendar. It served as a guide. But over time, the relationship changed. Observation gradually became investigation. In 1943, Nicolaus Copernicus published the work that placed the sun at the center of the known planetary system. The correction was mathematical, yet its consequences extended much further. Humanity no longer occupied the geometric center of creation. Instead, we became one world moving around a star. Centuries later, new tools deepened that understanding. Spectroscopy, the study of light separated into its component colors, allowed scientists to identify elements inside distant objects. By examining sunlight from Earth, researchers determined the sun's chemical composition without ever touching it. One element, helium, was discovered in the sun before it was identified on our own planet. Its name came from Helios, the ancient Greek personification of the Sunday. Knowledge accumulated slowly, generation by generation. Observation became measurement. Measurement became theory. Theory became prediction. Then prediction became exploration. The Parker Solar Probe belongs within this long continuum. It is not separate from the monuments, calendars, and observations that came before. It is their distant descendant. For thousands of years, humanity watched the sun, interpreted it, measured it, and sought to understand it. Then, at last, a human creation crossed into its atmosphere. The long act of looking became an act of contact. There is a quiet idea running beneath every scientific mission. It is older than rockets, older than telescopes, older even than written language. The idea is simple. If nature follows rules, then those rules can be discovered. Physics grew from that belief. At its heart, physics is the search for the principles that govern matter and energy wherever they exist. Stars provide one of the most demanding places to test those principles. Within them, temperatures rise to extraordinary levels. Magnetic fields twist across immense distances, and charged particles move through environments unlike anything naturally available on Earth. Yet the rules remain the same. The processes Parker measured deep within the sun's atmosphere: magnetic reconnection, meaning magnetic field lines breaking and reconnecting; plasma wave propagation, meaning waves traveling through electrically charged gas; and particle acceleration, meaning particles gaining enormous energy, all operate according to laws that also govern laboratory experiments conducted on Earth. The scale changes dramatically. The principles do not. This is one of the most remarkable features of the universe. A law discovered through a small experiment can describe phenomena occurring across millions of kilometers. The same mathematics used to explain behavior inside a laboratory can help explain activity inside a star. Because of this universality, understanding one star in detail becomes something much larger than understanding a single object. We are testing whether our descriptions of reality continue to function under conditions far beyond everyday experience. Every successful prediction strengthens confidence that the underlying framework applies everywhere else as well. But science does not advance only through confirmation. Sometimes it advances through surprise. When Parker encountered structures, flows, and magnetic behaviors that existing models had not anticipated, the discovery did not imply that physics had failed. The laws remained intact. What changed was our understanding of how those laws interact under solar conditions. The equations were still there. The interpretation needed refinement. That distinction matters. Scientific progress rarely arrives as a complete replacement of knowledge. More often, it arrives as additional detail. A model becomes sharper, a prediction becomes more accurate. A gap becomes visible where none had been noticed before. Incompleteness is part of the process. Every answer reveals new contours beyond it. The sun occupies a special position within that process because it is the only star close enough for this level of investigation. Other stars fill the galaxy in astonishing numbers, perhaps more than 100 billion within the Milky Way alone. We can observe their light, estimate their temperatures, measure their motions, and infer their composition, but none can be examined with the intimacy available here. The sun serves as our detailed example, our reference point, our translator. For generations, astronomers have treated it as the key for interpreting distant stellar observations. Parker has made that key more precise. It has added texture where there was once approximation and direct measurement where there was once inference. In doing so, the mission has sharpened the instrument through which we understand not merely our star, but the countless stars scattered across the wider universe. Imagine beginning not with Earth, but with distance itself. At Parker's closest approaches, our planet lies roughly 150 million kilometers away. From that vantage point, Earth is no longer recognizable as a world. There are no continents, no oceans, no clouds, no sign of cities, civilizations, or history. There is only a faint point of light, so small and dim that it blends among countless other distant lights scattered across the darkness. You could easily miss it. From deep within the sun's outer atmosphere, the solar system presents a very different appearance from the one familiar to us. The planets do not dominate the view. They do not announce themselves as destinations. Instead, they occupy isolated positions within a vast volume of mostly empty space, separated by distances so large that the architecture of the solar system seems sparse and delicate. The surrounding environment feels stranger still. The corona, the sun's outer atmosphere, is not empty. It glows softly in visible light. Diffuse plasma extends through immense regions of space, creating a faint luminosity that stretches millions of kilometers beyond the visible solar surface. Parker travels through this environment directly. Rather than observing it from afar, the spacecraft moves within it, surrounded by material that remains gravitationally connected to the star. In that setting, Earth becomes something abstract. Not a landscape, not a home, a coordinate, a location where a thin layer of atmosphere surrounds a rocky planet orbiting far from the intense conditions near the Sunday. Everything familiar to us exists within that tiny point. Every language ever spoken, every species that has lived, every triumph, failure, discovery, and memory, all contained within something that appears no more significant than a distant star. But the relationship between Earth and the Sun remains profound. The Sun does not direct special attention toward our world. Solar wind flows outward continuously. Magnetic eruptions occur when conditions permit. Coronal mass ejections expand through space according to physical laws that operate without intention or preference. The nurturing and the danger arrive together because they emerge from the same underlying processes. A star simply behaves as a star. Hydrogen becomes helium through nuclear fusion. Energy moves outward. Magnetic fields form and evolve. Plasma escapes into surrounding space. Earth receives the consequences of those processes because it happens to orbit nearby. From a stellar perspective, if such a perspective can even be imagined, the entire history of our planet occupies only a tiny corner of a much larger system. Yet Parker introduces a remarkable reversal. The spacecraft was designed on Earth, built from earthly materials, and launched by earthly hands. Every sensor, circuit, and measurement originated here. In a very real sense, Parker is Earth extending itself outward, a small world reaching across space toward the star that shaped its oceans, powered its climate, sustained its biosphere, and made every living thing possible. Some journeys end with an arrival, others end by revealing how much further there is to travel. The Parker Solar Probe belongs to the second kind. With each completed orbit through the middle years of the 2020s, the spacecraft moved deeper into the Sun's outer atmosphere. Every close approach carried it through regions no instrument had previously explored. Each pass returned measurements from environments that had existed beyond direct reach for the entirety of human history. Yet the closer Parker traveled, the more detail emerged, and with detail came new layers of complexity. The story did not become simpler, it became richer. The mission's final planned encounters bring the spacecraft as close to the Sun as its designers intended, but Parker will not return home when those encounters are complete. No recovery mission waits for it. No retrieval has been planned. Long after its scientific operations eventually cease, the spacecraft will remain in orbit around the Sun, circling silently through space as a permanent artifact of human curiosity. Its work will continue, not aboard the spacecraft itself, but here. The information already gathered represents an archive so extensive that scientists expect to spend years examining it. Research papers, based on Parker observations, will continue appearing well into the decade of the 2030s. Hidden patterns, subtle relationships, and unexpected discoveries may still be waiting within measurements that have already been transmitted across space. At the same time, other missions carry the investigation forward. Solar Orbiter continues its campaign to observe regions Parker could not directly examine. Its views of the solar poles will help complete a picture that no single spacecraft can assemble alone. Together, these missions are transforming our understanding of the nearest star. And they are unlikely to be the last. Engineers are already studying concepts inspired by Parker's success. Future spacecraft may travel even deeper into the corona, approaching distances below 5 solar radii from the solar surface. The architecture pioneered by this mission has shown that journeys, once considered impossible, can become practical engineering challenges. Many of the questions that launched Parker have now been answered in broad outline. We understand far more about coronal heating, magnetic energy transfer, solar wind formation, and the dynamic structure of the Sun's atmosphere than we did before the mission began. But understanding is never a finished state. It is a process of refinement, a continuing conversation. But beneath the scientific achievements lies another question, one that cannot be resolved through measurements alone. What does it mean that a species, which has existed for roughly 300,000 years, on a planet about 4.6 billion years old, orbiting a star older still, has reached outward and touched that star? The answer is not contained within any instrument reading. It exists in the choice itself. The decision to imagine such a mission, to build it, to send it toward overwhelming heat and distance, and then to wait through long silences for proof that it survived. We touched the Sunday. What we found was knowledge, but we also found a reflection of ourselves, a reminder that every frontier crossed reveals a horizon beyond it, and that curiosity remains one of the most powerful forces our species possesses.